Assalamu alaikum and welcome to lecture 14 of data structures and algorithms. Today we are going to talk about stacks. We are going to use chapter 7 of book 1 for this topic. In the last lecture, we were introduced to stacks. We implemented stacks using the Python list and the singly linked list. We listed several problems that use stacks for solution. We learned about different formats for mathematical expressions. We learned how to convert between formats, and we learned how to evaluate postfix expressions. The problem with infix expressions. We work with infix expressions on a regular basis and find them rather easy to evaluate, but the task is more difficult for a computer program. A mathematical expression is represented as a string in the computer. Consider the expression A multiplied with B plus C divided by D. As we have already discussed, this is an infix expression. Now, your teacher in school has taught you the BODMAS rule. He or she told you that first you open the bracket, then you divide, then you multiply, then you add, then you subtract. And since you are a human being and human beings are very intelligent, you look at the expression and you find out that since the divide sign is present somewhere, that operation has to be done first. You don't get bothered by the fact that the divide sign is at the end of the expression, because you are mentally looking at the whole expression. But a computer scans a string from left to right. I show you the direction with an arrow. When evaluating this expression stored as a string and scanning one character at a time from left to right, how does the computer know the addition has to wait until after the division? Surely the computer cannot know. Since the computer does a single left to right scan of the expression string, it requires a representation in which the operators appear in the order they should be performed. This is the problem with infix expressions. The computer cannot use the BODMAS rule because it is scanning the string character by character. So we need to write our expressions in a format such that the higher precedence operators appear first, and if they appear first, then they get evaluated first. Also, the computer does not know how to locate the brackets and open them first. So this means that the infix expressions are good enough for us, but the computer has a lot of problems with them. In infix notation, the same expression can bear multiple meanings with the use of parentheses. In the postfix and prefix notations, each expression is unique. You can see that the postfix notation for an infix expression without brackets is different than the postfix notation for the same infix expression with brackets. The postfix and prefix notations do not use parentheses to override the order of precedence. So the computer's work is minimized. It does not have to worry about brackets. There are no brackets in postfix and prefix. So with these points in front of us, it is clear that The computer is more comfortable with the postfix or prefix notations, not as much with the infix notation. Then why we move to the postfix notation only? The final answer is, in the postfix notation, the scanning program gathers the operands before the operation, which is the norm for all procedures. Every function that we write, we first provide it data in the form of arguments, and then inside the body of the function we implement what it is supposed to do. And that is the logical path that we take in postfix notation. We first gather the data and then we operate the data. So all computers use the postfix notation to handle mathematical expressions, while nearly all humans use the infix notation for the same purpose. I present to you the algorithm for evaluation of postfix expression. 1. Initialize an empty stack. 2. Repeat the following until the expression ends. A. Get the next token or character of the expression. B. If the token is an operand, push it onto the stack. Otherwise, it is an operator. Do the following. 1. Pop from stack and call this B. 2. Pop from stack and call this A. 3. Apply the operator to these two values. Result is A token B. 4. Push the resulting value back onto the stack. 3. When the end of the expression is encountered, its value is on the top of the stack. It must be the only value in the stack. Otherwise, your postfix expression was wrong. Now, the algorithm is written here on the side, and I am going to show you how I use this algorithm to evaluate the postfix expression that is written in front of us. Each character in the postfix expression is a token. I take the first token, which is 1. Since it is an operand, I push it onto the stack. Then I have 2. Since it is an operand, I push it onto the stack. Then I have minus. So I pop 2 from the stack. Then I pop 1 from the stack. You can see B is 2, A is 1. The result is A minus B, which is minus 1. And I push the result back onto the stack. I repeat this. First I popped 2, then I popped 1. So the stack is empty. Then I computed the value and I pushed minus 1 on the empty stack. So now the stack has minus 1. 4 is an operand, so I push it onto the stack. 5 is an operand, so I push it onto the stack. Now I have the caret sign or the power sign. So this is an operator. I pop the first element 5, this goes into B. Then I pop 4, this goes into A. The result is 4 raised to 5, A raised to B, which is 1024, which I push back onto the stack. Notice that I popped 5, I popped 4, but minus 1 was there on the stack. When 1024 goes into the stack, it goes to sit on top of minus 1. The next thing is 3, which is an operand, so I push it onto the stack. Then I have the multiply sign. So I pop 3, it becomes B. I pop 1024, it becomes A. The result is 1024 multiplied with 3, which is 3072, and that I push on top of -1 onto the stack. Next, 6 is an operand, so we push it onto the stack. Then multiply is an operator. B is 6, A is 3072, R is A multiplied with B. This is 18432, which we push back onto the stack. Next is 2, which I push onto the stack. Then we have another 2 that also we push onto the stack. The next token is 2, which is an operand, so we push it onto the stack. Now we have a power sign. Pop 2, this becomes B. Pop 2 again, this becomes A. The result is A raised to B, which is 4. Push it onto the stack. Another power sign. Pop 4, this becomes B. Pop 2, this becomes A. The result is A raised to B, which is 16. Push it onto the stack. Now we have a divide sign. Pop 16, put it in B. Pop 18432, put it in A. The result is A divided by B, which is 1152. Push it onto the stack. The last token is a minus sign. Pop 1152, this is B. Pop -1, this is A. The result is A minus B, which is minus 1153. Push it onto the stack. Since there are no more tokens in the expression, we come out of step 2. In step 3, we are told to pop one element from the stack, which will be the evaluated result of the postfix expression. In our case, the result is minus 1153. So let's do a complexity analysis. In step 1, the init function is called for the class that implements the stack. It takes O1 time. Step 2 has a loop that runs as many times as the number of tokens or characters. Let the number of tokens be n. In other words, n is the length of the postfix expression. If the token is an operand, we push it in O1 time. If the token is an operator, we pop twice, compute and push. Pop is O1, compute is O1, push is O1. So we get O1 plus O1 plus O1 plus O1. The whole time that we take when the token is an operator is O1. So this means that the body of the loop in step 2 takes O1 time whether the token is an operand or an operator. But we also noticed that the loop executes n times. So n multiplied with O1, step 2 takes On time. Step 3 encompasses a pop operation which takes O1 time. Now we add the notations of steps 1, 2 and 3 because they are appearing one after the other. The final O notation of the algorithm is On. Space complexity of an algorithm. Space complexity is asymptotic analysis of the space used by an algorithm to solve a problem. We consider how an algorithm's memory requirements increase as the input size increases. We investigate the additional variables and data structures that an algorithm uses to solve a problem, the space occupied by the input to the algorithm is not considered in space complexity analysis because that cannot be avoided. You cannot run an algorithm without providing it any input. So we only consider the additional variables, not the memory taken by the input that is provided. Space complexity of the algorithm for evaluation of postfix expression. In any postfix expression composed of binary operators, there are x operators and x plus 1 operands. Whatever is the number of operators, the operands are always one more. Let the length of the postfix expression be n. Then n will be the number of operators plus the number of operands. From here we can say that x is n minus 1 whole divided by 2. What do we keep on the stack? We keep operands on the stack in the algorithm for postfix evaluation. And the number of operands is x plus 1. So the maximum size of the stack would be equal to the total number of operands, x plus 1. X plus 1 is n plus 1 whole divided by 2. So I can say that the maximum size of the stack for n elements would be n plus 1 whole divided by 2. From here, the O notation of the space taken by this algorithm is On. Algorithm for conversion from infix to postfix expression. 1. Initialize an empty stack. 2. Repeat the following until the expression ends. A. Get the next token of the expression. B. If the token is 1. A left parenthesis, push it onto the stack. 2. A right parenthesis, pop and display stack elements until a left parenthesis is encountered but do not display the left parenthesis. 3. An operator. If the stack is empty or token has a higher priority than the top stack element, push token onto the stack. A left parenthesis in the stack has lower priority than all operators. Otherwise, pop and display the top stack element, then repeat the comparison of token with the new top stack element. An operand, display it. 3. When the end of the expression is encountered, pop and display stack items until the stack is empty. Precedence levels of operators. The highest precedence level is that of the power function, followed by the next level which has multiply and divide signs, and the lowest precedence level is that of the plus and the minus signs. Let us now convert the given infix expression to a postfix expression using the algorithm which I have placed on the left. Keep in mind that the stack we are using will only hold the operators, never the operands. When we begin, the stack is empty. 2 is the first token, and since it's an operand, we display it. The next token is the power sign. Top of the stack is not present because the stack is empty. Power sign is an operator, so we push it onto the stack. Next is 3, which is an operand, so we display it. Next is the multiply sign. R token is the multiply sign. Top of stack is the power sign. Does R token have a higher priority than the top of the stack? No. So we pop the top of the stack and display it. You can see that the power sign is at the output now. After we have popped the power sign, the stack becomes empty. What do we do with our token? Since the stack is empty, we push it onto the stack. Next is 7, which is an operand, so we display it. Next is plus. Our token is plus. Top of the stack is multiply. Does our token have a higher priority than the top of the stack? No. So we pop the top of the stack and display it. You can see it at the output. Now the stack is empty, so we push our token onto the stack. Next is a left parenthesis, so we push it onto the stack. Next is 5, an operand. We display it. Now we have minus. Our token is minus. Top of the stack is left parenthesis. Does our token have a higher priority than the top of the stack element? Yes. So we push our token onto the stack. Next is 4, which is an operand. So we display it. Next is a right parenthesis. We are going to pop and display stack elements until a left parenthesis is found. So we pop minus, add it to display. Then we pop the left parenthesis, but the left parenthesis is not displayed. So the remaining things on the stack now are the plus sign only. Next we have a multiply. This is an operator. Our token is multiply. Top of the stack is plus. Does our token have a higher priority than the top of the stack? Yes. So we push our token onto the stack. 15 is an operand, so we display it. Now we have a token divide. Top of the stack is multiply. Does our token have a high priority than the top of the stack? No. Pop the top of the stack and display it. Minus sign is displayed. Now the top of the stack is plus. Does our token have a high priority than the top of the stack? Yes. Push the token onto the stack. 3 is an operand, so we display it. Now we have minus as the token. Top of the stack is the divide sign. Does minus have a high priority than the divide sign? No. Pop the divide sign, display it. Now the top of the stack is plus. Compare the priorities of minus and plus. Does minus have a high priority than plus? No. Pop plus and display it. The stack is empty. Push minus onto the stack. 8 is an operand, so display it. We have run out of tokens in the expression. Step 3 says, when the end of the expression is encountered, pop and display stack elements until the stack is empty. So we pop minus and display it. The stack is now empty. 2, 3, power sign, 7, multiply, 5, 4, minus 15 multiply 3 divide plus 8 minus is the converted postfix expression. Instead of a character by character display, we can append each character that we want to display to a Python list and then print the list out at the very end. Now we talk about the worst case time complexity of this algorithm. In step 1, the init function is called for the class that implements the stack. It takes O1 time. Step 2 has a loop that runs as many times as the number of tokens. Let the number of tokens be n, or n is the length of the given expression. If the token is a left parenthesis, we push it in O1 time. If the token is a right parenthesis, we pop several times, say x. We need to know what the maximum value of x is to determine worst case complexity. If the token is an operator, we compare it with the top stack element several times, say y, before we push the token onto the stack. We can only push a higher priority token over a lower priority token. There are 3 levels of precedence for operators. This means we can have 3 operators of different priority levels in the stack consecutively. For example, you have a minus sign on which you push a divide sign on which you push a power sign. We can have more than 3 operators in the stack, like the example I've shown here. So I am not saying that the maximum number of operators is 3. I am saying that the maximum number of consecutive operators is 3. In this example, you see that you have 2 operators, then you have a left parenthesis, and then 3 operators. So consecutively, we will have 3 operators, not more than that. One for each level of precedence. If we can push 3 operators in the stack consecutively, the maximum number of comparisons y, which we need to do for an operator, is 4. 3 comparisons with operators and the last comparison with the left parenthesis. The maximum number of pops when we encounter a right parenthesis x is 4, as we need to pop 3 operators and a left parenthesis. Consider the last subpart of 2b. If the token is an operand, it will be displayed in O1 time. In the worst case, the token will be compared 4 times before being pushed in the third subpart of 2b, no matter what the value of n is. Since the number of comparisons is independent of the value of n, and we are doing asymptotic analysis, so the value of n is going to be very large, we can say that the comparisons happening are O1 in time, because they are not changing as n is changing. In the worst case, 4 elements will have to be popped when a right parenthesis is seen, no matter what the value of n is. This is with reference to the second subpart of 2b. Again, the popping that takes place for a right parenthesis is independent of the value of n, and we consider it to be O1. So the body of the loop in step 2 takes O1 time in all cases. But step 2 iterates n times. So step 2 takes O(n) time. Step 3 encompasses 4 pop operations in the worst case, 3 operators and then a left parenthesis, no matter what the value of n. Again, the value of n is going to be very large for asymptotic analysis. So we say that step 3 takes O1 time. Step 1 takes O1, step 2 takes On, and step 3 takes O1 time. So the final O notation of the algorithm in the worst case is On. Space complexity of the algorithm for conversion from infix to postfix expression. In any infix expression composed of binary operators, there are x operators, x plus 1 operands, b left parentheses, and b right parentheses. Obviously, we will have as many left parentheses as there are right parentheses. Let the length of the postfix expression be n. Then n will be equal to the number of operators plus the number of operands plus the left parentheses plus the right parentheses. From here I can say x plus b is n minus 1 whole divided by 2. So what do we keep on the stack in this algorithm? We keep operators and left parentheses on the stack in the algorithm for conversion from infix to postfix expression. So the maximum size of the stack is x plus b, the value I have already given you. From here I can say that the memory taken by this algorithm is On. You have seen this homework before. This is the slide of the tasks that I set you in the previous lecture. There I was asking you to do these things by hand. Now I ask you to do the same thing using algorithms and stacks. Homework 1 says convert the following infix expression to postfix using a stack. Homework 2 says evaluate the given postfix expression using a stack. Run the algorithm with these inputs and in the end, check your answer with the answers in the previous lecture to see if you've done it correctly. Homework 3 is to implement the algorithm for postfix evaluation in Python. 4 is to implement the algorithm for conversion from infix to postfix expressions in Python. So what did we learn today? We discussed the reasons behind preference of postfix expressions for computing machines. We traced through the algorithm for postfix evaluation. We traced through the algorithm for conversion from infix to postfix expression. And we investigated the complexities of the algorithms discussed. In the end, things to do for you. Read the book, note your questions and put them up in the online session and email your suggestions to me. Do email me your homework so that I am able to see what your problems were and how you've solved them. Take care. Allah Hafiz.